Our speaker for today is Professor Wei Yu. Professor Yu, originally from Anhui Province, China, is the Carrie C. Boschhammer Distinguished Professor of Chemistry at the University of North Carolina at Chapel Hill. He earned his BS from the University of Science and Technology of China and his Ph.D. from the University of Chicago, followed by postdoctoral training at Stanford University. Professor Yu has published over 200 papers in premier journals such as Nature Materials, Nature Photonics, JACS, Agavante Chemi, Macromolecules, Advanced Materials, among others. He is currently serving as an associate editor for the journal ACS Polymer Science and Technology and also an associate editor for the RSC journal Polymer Chemistry. He has also served on the advisory board for ACS Macromolecules and ACS Applied Energy Materials. He has received DuPont Young Professor Award, NSF Career Award, Camille Dreyfus Teacher Scholar Award, Tanner Award for Excellence in Undergraduate Teaching, CAPA Distinguished Junior Faculty Award, Ruth and Philip Hettelman Prize for Artistic and Scholarly Achievement, and World Highly Cited Researchers by Web of Science Group. He is a Fellow of Royal Society of Chemistry and Fellow of the American Association for the Advancement of Science. His research focuses on novel conjugated polymers for optoelectronics, new polymerization methods, hybrid 2D perovskites. So thank you, Professor Yu, for joining us here today. The stage is all yours now.
Thank you very much, Neha. Let me try to share my screen so we can get things started.
Perfect.
Okay, all right. So give me 1 second. I want to be able to, where's the little, okay, got it. So laser pointer just in case I need. All right, thank you everybody for signing up this interesting webinar. I personally never done this sort of the facing general audience webinar in the past. So this is going to be an interesting time for myself and as well. And I spent maybe 10 plus hours to create some more general audience facing slides. So you will see in the next few, say 10, 20 slides. So we're going to try to go with the very simple ideas to make sure everybody will be on the same page. And before we go and dive into the details of our research. So this is a roadmap for today's talk, and I'll be talking maybe 10, 15 minutes about the fundamentals, and then 5 minutes about the field landscape, and basically what has been done for this particular topic. Then I'll spending maybe 20 minutes going over our approaches for this particular topic. So if you never heard about the conjugate polymers, and you possibly not alone, and many people I talked to my parents, so they were curious about what I was doing, and I tell them that, well, this is what I work in the conjugate polymers. They possibly don't even know what a polymer is, right? So, but the reality is that we are using conjugate polymers, or like maybe broadly defined as so-called organic electronics or plastic electronics, pretty much every day. So this, on the top left, this is actually a sort of a flip phone, which I have one, and in my pocket. And the reason that you can make them foldable, flippable, because you have the organic or plastic electronic components on the screen in many parts of the phone as well. So if you know about this one, you say, yeah, I have this one in my pocket, I can use it every day. But now I'm going to show you something even more interesting, right? So traditional electronics, you possibly make them from, say, silicon, germanium, et cetera, they usually are pretty brittle, okay? So with the plastics, electronics, you can make the screen like a razor thin, and also they make it very flexible as well, because at the end of the day, it is a plastics, right? So we spent maybe like 20 plus years, and many people as well, and working on something we call the organic solar cells, and the reason you can make them almost flexible, stretchable, all these nice features you will now be able to have from the traditional silicon-based electronics, because they're polymer-based. So this is just one of the solar cells that people were able to make in the lab, and we actually made something like that in the lab as well. Now, this is really futuristic. You can't do that. I think this one is possibly more illustrating about the power of the plastics. And you can see that you can wrap around your wrist. You can try to just roll it up and push the button and all these things like you only being able to see in the, in the sci-fi movies. And now all of a sudden showed up, your girlfriend is waving to you, going through some transparent screen. And this is all because you can actually using the organic semiconductor, or sometimes we call the plastic electronics, okay? So speaking of which, then conjugate polymers are actually core to the plastic electronics. And on the simple idea, you may say, oh, yeah, I know about the plastic electronics. So what do we do is, so we take the plastics, we take the electronics, we put them together, it's plastic electronics. Well, it's not that simple, okay? So because there are many ways, many reasons, many things that we would have to do before we can enjoy the benefit of the both plastics and the electronics. So what do we do? Okay, so from the chemistry, very simple chemistry, right? So you all understand that this thank you plastic bag most likely made from the low density polyethylene, right? Polyethylene, possibly the simplest polymer ever. You learn from maybe the, Argo 1, for example, maybe polymer chemistry when you were in college. It's a pure hydrocarbon, right? So it's CH2, CH2, CH2. Very simple. It's all single bond. And this is the polyethylene. You cannot make a polyethylene conducting, period. Okay. But the chemistry people back in the days, they were smart enough. If you still remember anything from your say organic chemistry first semester, you will realize that there's something we call the pi electrons. Okay. So what we do is that if you taking away some of the hydrogens from the polyethylene, and then you create a double bond, right? So all of a sudden you would have a single bond, a double bond alternating. This is what we call the polyacetylene. Keep in mind that this is not a polyethylene, because a lot of the people will be thinking, oh, this is polyethylene because the building block is ethylene, which is untrue, because when you're using ethylene making the polymer, you basically open up the double bond and become a single bond. But in the case of this particular polymer, we call it polyacetylene because you take the acetylene, which is a triple bond, you open up, you link them all up, and now all of a sudden you would have the single bond between the CC double bond. That's why we call it polyacetylene, because the name is coming from the monomer the polymer was made from. So polyacetylene is very unique. Every time I look at this one, this is the like, oh, very good, because now I have unsaturated bond and alternating, it's perfectly delocalizing. I'll have electron going through the entire orbitals. I have a very good conductivity. That intuitively is correct, okay? So if you look at in here, is I'm going to be more chemistry. And if you look at all the carbon-carbon bond, single bond between them, and you have all the pi pz orbitals perpendicular to the plane, and they all overlap, right? So back in the days, we call the shoulder-to-shoulder interaction, and you have a delocalized pi bond. That's where the electrons can move, electron clouds will be able to distributing across the entire molecule, then you have the possibility to conduct electricity, okay? But having the polyacetylene alone will not give you the conducting polymer. It is a semiconductor. I don't want to go through all the details of why this particular polymer is not going to give you the band gap zero, for example. But the way you can make them conducting is that you going something very familiar to the chemistry people we call the redox, okay? What you do is that you take the neutral polyacetylene, you do, for example, you do the oxidation, you're using oxygen to take one electron away from polyacetylene, then all of a sudden you would have a so-called radical cation. Okay, this is a radical cation. In the traditional polymer, in the traditional conjugate polymer, we possibly have something we call the polaron, but in the polyacetylene case, there's something special called solitol. But that's not the point of this talk. So fundamentally, you're creating a radical cation. All of a sudden, you would have a mobile charge carrier. If you further doping, you'll be going to something we call the bipolaron. But the point is that by using doping, redox chemistry, you're creating mobile charge carriers on the polymer. And then plus you have a delocalized pi bond, and all of a sudden now you can talk about a conducting polymer, because you're not only having the electron holes on the polymer, you can actually have a delocalization that allows you to have the transporting the charge carrier through. That's the conductivity. Okay. So because of that, this was discovered in the late 1970s, 1978, 1977. And many years after, these are three gentlemen who were the discoverers of this phenomenon, right? Alan Heeger, Alan McDermott, and Shirakawa. They received a Nobel Prize in 2000 and for the discovery of the polyacetylene, or we call the conducting polymer. So if you go back to your organic chemistry, you realize that, well, if you only want to have the pi electrons, polyacetylene, of course, is very good. You have a bunch of pi electrons and p orbitals lined up. And we have something we call the benzene, right? Benzene ring, essentially, you have 6 carbons, and each one of them has pz orbital. You have delocalized pi electron as well. So once you introduce the benzene or aromatic units, you expanded the scope of the conjugate polymer tremendously. Okay, if you look at it here, is the polyacetylene is the first one. Now, if you put in the phenylene or like benzene ring into the system, we call it polyparaphenylene. Then you have polypyrrole, polyfuran, polyethylene, et cetera, et cetera. You can make something even more complicated, right? So you can make some polyfluorine, for example, or polycarbazole, polyphenylvinyl, et cetera, et cetera. So this is now all of a sudden chemistry people like myself who are really interested in designing the materials, and we have a very fertile playground because we can create all sorts of interesting materials from these building blocks. So this is the polyethylene. I just give you a simple idea, right? It's polyethylene, the neutral state is right in here. If you can also having things we call the quinoidal state, which is very interesting because if you're taking away the ethylene, this is essentially a polyacetylene in the cis version, right? Polyacetylene has cis and trans. This is the polyacetylene in the cis version. You bond the unit between by using solving, right? So this is the polyethylene sulfur, sorry. So then if you do the redox chemistry, same trick I talked about earlier, then you will be able to creating the radical cation on the ethylene, or you're making a polaron, bipolaron, et cetera, and you are able to make the conjugate polymer conductive. So if this is the possible more visualizing, you can see all the pz orbitals lined up, they all delocalize, and et cetera, and you will be able to have a conjugated polymer. Once you dope them, you have a conducting polymer. I want to emphasize that a neutral conjugated polymer are not conducting polymer. If you try to make it a conducting polymer, you would have to create the charge carriers onto this conjugated polymer, then you will be able to conduct it because of the intrinsic, which we'll talk about later, the intrinsic conductivity of the carrier density for the conjugate polymer is actually pretty low. That's why you won't be able to get any sort of the meaningful conductivity. So up until this point, I possibly spend the most time talking about the conjugate backbone, which in my understanding is where the most people care about. It's very simple, very understandable because by tuning the conjugate backbone, you essentially manipulating the optoelectronic property of the material. So let's say if you try to make a smaller bandgap, for light harvesting, maybe for the IR sensor, for the, I see a lot of people using the conjugate molecules, the conjugate polymers for the biosensing, right? So you want to be able to go to the wavelength, let's say 1 micron or 1500 nanometer. And that way you can actually have a deep tissue penetration. You will be able to see the, what happens inside your body. So backbone is always the first priority because that's where most chemistry is happening, and because we want to be able to manipulate the optoelectronic properties. But on the other side, we also spend a lot of time trying to tune the side chains because if you do not have a side chains, your conjugate polymer will not be able to solution processable, which we'll talk about in the next slide. Then sometimes we'll be putting on the substituent to further modulate the electronic properties, and we also want to be able to tune the so-called intermolecular interaction or intramolecular interaction in order to change the properties in the solid state. So by changing the backbone, you can literally get going to any color you want because we know how to manipulate the optoelectronic properties, especially optical in this particular case. And this is not a picture that I just got from Google. This is actually all the polymers we ever created in my lab in the past 15 years. Some time ago, we collected all the different materials we created. We put in the vials. It's really good for the general public education. You can see that plastics, not just having the transparent, no color or white color. You can actually make them into the different colors if you know the chemistry, how to tune them. So now the next thing is that, well, the topic for today is not about the conjugate backbone. It's about a side chain. So why side chains are indispensable? Very simple reason, because the reason you want to be able to use the polymer for electronics is because, first of all, you can make the material in the cheap, in theory, cheap synthetic methods. And then the second thing is that you want to be able to dissolve them into the processing solvents. So then in that situation, you don't have to use a high temperature, energy intensive process like silicon processing. And you can literally just print a newspaper. Okay. If you try to make a printed newspaper, and you need possibly the ink, so-called ink, otherwise you won't be able to do the solution process away. So this is essentially the same thing we do with the conjugate polymer. You take the conjugate backbone, you decorate them with a side chain, and you will all of a sudden be able to make them solution processable. Depending upon which side chain you put on, decorate the conjugate polymer, you can possibly even achieve the water solubility, right? That would be ideal because any organic solvent possibly having some issues to the environment. You may want to go to the alcohol or like ultimately go to water. We have done something like that as well. So then you took it for granted, myself too, right? So we often say, oh yeah, conjugate polymer need side chains because you want to make them solid. But why? You actually think about why side chains are making conjugate polymer soluble, right? So if you think about that, it's actually a very interesting question. Um, so if you do not get to the answer right, well, I'll give you one simple example. So I think many people possibly understand the graphing, right? So this is the wonderful material that we literally using every day because when you're writing on the piece of paper with a pencil, and that's graphite, and that's actually a layered graphene materials. So 20 years ago, 22 years ago, and these folks in Manchester were able to take the Scotch tape, peel off the graphene, and showing that you have a nanometer thick material, and it's beautiful. It's zero band, semi-metal. It's a beautiful conductivity and for many applications. But keep that in mind that graphene itself is actually not soluble. It's virtually insoluble in any solvent. Why? Because all these beautiful 2D sheets, they actually have essentially a delocalized pi orbital. Then from one graphene layer to the second graphene layer, you have a very strong so-called pi-pi interaction. I know some people do not like to use the term anymore. There's a paper in JAX talking about the pi-pi interactions, and this term is too loose. But I just still use that for the sake of discussion. So once you have a very strong interaction, that's where the graphene layers would have to be physically separated by some other means. One way you can do that is to essentially oxidize the graphene. You're creating all the defects, and you're breaking the conjugation. You're creating the so-called graphene oxide, and then you will be able to disperse that into water. So, but then all of a sudden you change the property of the graphene. So same idea is if you virtually slicing graphene into the one repeating aromatic ring, the so-called graphene nanoribbon, they are not soluble either. But that's essentially the precursor of the conjugate polymer. This is also the reason why conjugate polymer without side chains are not soluble, because they have such a strong pi-pi interaction. You need somehow to break them. So when we put a conjugate side chain to the conjugate polymer, you essentially help facilitating the peeling off the different conjugate, say stop the weakening the intermolecular interaction to allow your conjugate polymer to be solution processable. So that's essentially so-called enthalpy argument. But in some other cases, you can also argue that because you have the flexible side chains, when they penetrate and dissolve in the solvent, you also increase the entropy. So to the minor contribution, but it's still a contribution. So in these cases, why side chains make the conjugate polymer soluble? Because you have a combination of the entropic effect and also the enthalpic effect and also the entropic effect. All right. So, but having side chain honest with you, and you actually bring quite a bit of the hidden cost. So first of all, if you do the calculation, the drawing possibly not illustrating this concept perfectly, but if you do the calculation, you realize that this is seemingly very benign, very small amount of the hexyl side chains to the so-called poly 3 hexylphenolphene, actually adding about 50% of the volume. And they're insulating, right? Because if you try to make the conjugate polymer conducting, you possibly want to be able to minimize the insulating components as much as you want. And so, but now you essentially suffer from the 50% of the insulating volume, and that's not good news. But we suck it up. We say, okay, we want conjugate polymer to be solution processable, so we need them. All right, so we just okay, we need to find some ways. So the second, which we spent some time to think through, is that having the side chain also brings some other detrimental, or let's say inconvenience, to the materials. First of all, is possibly the TG glass transition temperature will be suppressed. I'll talk about in a few seconds. And the second is you actually having the side chains, you disrupt the pi stacking, which you possibly need for the charge transport. But they also, back to my earlier point there, that you do want to have a side chain to break them to a certain extent. Otherwise, you won't be able to dissolve them, right? So then third is now you have a ceiling on the conductivity because you are not having 100% conjugate polymer in your finished film because 50% is essentially insulated. So I want to spend some 10 seconds on TG. So this is the equation, the Gordon-Taylor equation. If you are in the polymer field, you possibly understand this particular equation pretty well. Essentially, a weighted fraction of this conjugate backbone. This is the backbone and also the side chain. So if you, Harold Ade and Enrique Gomez and a few others have done very nice work to illustrate the point of the having side chain that will reduce your glass transition temperature. So let's take a look at this particular figure, which I took from one of the papers cited on here. Is that this is the weight fraction of this side chain. So if you have no side chain, your conjugated polymer is actually not that bad. You can have a glass transition temperature over like 150 degrees C, which is very robust. If you try to use a conjugate polymer, say very often that for the high temperature application, you possibly want to have TG as high as you want, as you can, like 150, 200 degrees C. Polyimide is really good, right? For example. But now if you just take a look at the either green or either blue or red curve, once you adding the side chain by 40%, 50%, you reduce the glass transition temperature from close to 500 Kelvin, now down to 350. Okay, all of a sudden, you reduce the TG by over 100 to 150 degrees C. That's a lot. Once you add in more and more side chain, of course, you essentially end up with the side chain only situation. That's essentially polyethylene or polyalkane, and you end up with below room temperature TG. So at the end of the day, you essentially do the weighted distribution of the high TG of the backbone and the low TG of the side chain. You end up with somewhere in here. If you try to make your solar cell electronic device very thermal resistant, you possibly want to have a high TG. So that's one of the reasons why we go after side chain cleavable materials. So now I bring the question is a side chain is absolutely necessary for the solution-based processing, right? Because that way you can dissolve them to make an ink. You can do the large area deposition. You can also control the packing, the solid state, and all the morphological features you can try to manipulate. But on the other side, because over 50% is insulating bulk, and now you have issues about the performance because 50% of the volume you have in the thin film not really contributing to your conjugated polymer why you're using them in the first place. So you have limited conductivity and mobility. So that's the fundamental issue we're hoping to address by using some interesting approaches, which we'll talk about in the next maybe 10, 15, 20 minutes. So what if we could have both, right? So you want to be able to process. Remember, side chain, you need them for the processing purpose. And this is the worm-like centipede, sorry to say that. And it's kind of like the conjugate polymer decorated with side chains. So you need them for the processing purpose. But now what if we can trigger apply some stimulus to remove the side chain. So then in the finished film, we will be able to have the side chain free conjugate polymer. So that would be ideal because in that when that happens, you have 100% of the conjugate backbone in the polymer film that should give you very high stability because the TG is high. It should give you high mobility because you have all the pipette stacking you want. In theory, that you will give you also the high conductivity because once you dope them, you have a higher charge carrier density and plus you have a high mobility and you will have a high conductivity. But of course, that is in theory, right? So to make that happen is not that straightforward. Right. So what this field has tried, this is not me starting this field. This actually has been worked on by many others, including myself, in the past 10, maybe 10, 15 years already. So I want to bring up this very nice review by Professor Bunz in Germany. This is the chemical review published about 7, 8 years ago now, which is a very long review, but it's absolutely worth reading because there are a lot of information, unless you are a specialist, you possibly either forgot or never knew of. For example, this particular one here is I've been honest, before I saw this particular picture, I already forgot about this concept. This is how people making the polyphenol vinyl back in the days, a long time ago. You're starting with something non-conjugated. Because non-conjugation, you have less pi interaction. You have very flexible, rather flexible side chains, stackable, so you can make them soluble. So that's why you don't need the long side chain in here. But now, if you're adding this very interesting solubilizing group by using heat or light, you can remove them. You end up with a side chain free conjugate polymer. And now you may say that, well, Dr. Yu, people already solved this problem long before you thought about this idea, which is true. But keep in mind that this is the early stage when people making the polyphenol vinyl, so-called PPV. If you're doing this approach, you very much likely end up with imperfect material because this particular step will never be 100% efficiency, which means that you will have a non-conjugation unit in your polymer. You don't even know where they are, then you absolutely end up with inferior material. You don't want that to happen, okay? Anyway, so I want to talk about 3 general approaches people are using. One is called the thermal cleavage. This is possibly most known to the audience in here, done by Bechet and Krebs and 20 plus years ago now. What they do is that they were taking this tertiary ester, making the polymer, then you're heating up to about 200 degrees C, and you will be able to remove this alkene and gone, and you end up with a carboxylic acid. It's become insoluble. This is the thermal approach. And people have using that for many years, and including my lab as well. This is one of the most recent papers published by Wan and co-workers. And they're using this approach on the N-type material. This is essentially the DPP, using the similar idea, tertiary ester, heat it up 200 degrees C, and you end up with this material in theory, and you will end up with insoluble and better performance. So the pros, including like no additive, you only need the heating. Because this approach is very benign, you can work with many different polymers, P and N type. But the bad news is that you do need a high temperature, 200 degrees C, 250 degrees C in some cases. That would be incompatible with many substrates. And also that because of high temperature, you're running the risk of affecting your mobility, your morphology of the finished film, right? So now then next thing people do is have tried is so-called photocleavable, right? So this is possibly the most useful unit for that purpose, which is pretty good looking molecule. I'll be honest, unless you spend some time working the molecule, it's not easy to draw this particular molecule. This is called orthonitrophenol, ONB functionalized. This particular molecule under the UV light, it can actually cleave. You end up with a carboxylic acid making the polymer insoluble. And then Sam Thomas and his labs are using this approach. They're being able to use the photolithography. So this is the one thing good about using photocleavable because you can do lithographically patterning the materials as you want. Use room temperature as well. But now, if you are in many cases, if you expose your conjugate polymer to UV light, keep in mind you have double bonds, and these bonds are easily susceptible to the UV damage. So then you end up with bad material, damaged material. That's not good for your performance if you're going after optoelectronics. And it's also a very slow process in the long exposure time. And then again, and you will be running the risk of damaging your film. Okay, so the last one is a so-called acid-base approach. And this is the one particular example was done by Professor John Reynolds' lab and also his student James Ponder. They published a few papers in the past few years and using this interesting ester. Okay, we all understand that ester can be using acid or base or hydrolyzed. So in this particular case, they're using the product and decorate with ester. They're using base to remove them in aqueous solution and methanol, then you end up with this particular material that's becoming side chain free, more or less. And then they were able to show that by using this approach, you can actually end up with a higher conductivity afterwards. So this seems to be a very good approach, right? But then the bad news is that you also need additives. And unless if you're using a water approach, you may be able to get rid of them in the solvent. But in many cases, they may actually stay in the film, which is going to affect your morphology and many other things as well. And then it's rather limited to the ester functionalized system. Okay, sometimes if you're using a strong base, you can degrade your polymer film and the backbone as well. So this is sort of the summary about the approaches the community has attempted in the past, 20 years, and thermal, photo, and base, and acid, anything you can think of, not anything. So most of the approaches you can think of, and we already tried in the field. Nothing is perfect. You have to choose the right one depending on your intended application as well. So in the next 10 minutes also, I'll talk about our approaches. And I think this is getting to the core of our research. So like I said earlier, that for the cleavable side chain, conjugate back polymer, ideally you want to be able to have the polymer stable during processing. When you apply the trigger, you can remove the side chain. You want to be able to have the clean removal because any residual, you may have to think about how the residual, organics will affect your morphology and many other interesting impacts that may coming from these residual organics. And you also want to be able to have the precise control and ideally programmable, because in some cases you want to be able to remove the side chain to 50%. Maybe some other cases you want to be able to remove the side chain by 100%, for example, and that's the idea. Okay, this is a wish list. It doesn't mean that I will be able to tell you the formula that will be able to fulfill all the things right away. But I'm hoping that down the road that we will, and together with the community, we'll be able to come up with better solutions for that purpose. So in the past 10 years or so, we have been working on using this cleavable side chain based conjugate polymers for 4 different areas. It can help you improve the doping and the conductivity. It can also enhancing the intrinsic stability of the organic solar cells. We also been strategically using them for stretchable multifunction sensors. And we also recently been able to use to achieve the unity doping efficiency in the OECT. I have a typo in there. And because of time limit, I'll be spending most of the time talking about the A and B in today's talk. So this is the first study that was done by Jordan Shanahan, who was a PhD in my lab. Now he's a Dr. Shanahan, and he graduated about a year ago. Now he moved on to working with the company now. So essentially what we've done here is that we're going to show you that even you are able to remove the side chain, but depending on how you process the film, you will see a huge difference in the obtained conductivity. Okay. Before we talk about the conductivity, remember back in the days that the resin polyacetylene got people excited because you can make them into a conducting polymer. Polyacetylene itself is a semiconducting polymer. It has very good mobility, but it doesn't have enough carrier density. Because if you try to making the conducting polymer conductivity, you essentially limited by the Charlie carrier density and also the Charlie carrier mobility. You want both numbers to be as high as you can if you want to get a really high conductivity. But you also have a limitation, which I'm showing next slide. So let's take a quick calculation. Suppose that you the carrier, density of conjugate polymer is roughly about a water density, 1 gram per centimeter square, the cube. The molar mass is about 500 gram per mole. So if you do the calculation, then you realize that the highest density of the carrier density is about the 10 to the 21st per centimeter cube. That's the highest. That's basically saying that when you have a one charge carrier per repeating unit, okay, that's very high. Assuming that you have a mobility 0.1, then if you do the math, you realize you can only get up to 10 Siemens per centimeter. That's a pretty low conductivity. It's still okay for the conductivity purpose, but it's still pretty low. But that's actually very high if you look at all these numbers. So if you're seeing someone achieving a conductivity 100, and then if you understand that there is a ceiling on the carrier density, that means that your mobility of your material must be very high, like so 1 centimeter. If you're seeing somebody achieve the conductivity 1,000, then the mobility of that particular process of film would be 10 centimeters squared per volt second. That's really high mobility if you're working the field. So then you say, okay, what about the inorganics, copper, right? So if you look at the copper is very interesting because it does not have a high mobility per se, because the mobility is about the 30. Okay, if you talk about 10, 30, rubrene can possibly making like 30, but their carrier density is very high. The reason is very simple, because the copper is atom-based material. And if each atom can contribute 1 electron, you're talking about almost this level, this carrier density. That is why copper have a very high conductivity, essentially like 10,000 Siemens per centimeter. Okay. So again, if anything you'll remember from this talk, I apologize, there are some fire trucks running by. And then we essentially need a high carrier density and high conductivity. Okay. So doping is very simple. For the chemistry people, we are talking about redox chemistry. Okay. If you have a dopant, the p-type doping means that you essentially have a dopant that's going to take an electron away from your polymer. That's p-type doping. If you have n-type, you have dopant pumping electron into the low mole of your conjugate polymer, you have n-type doping. So that's about it. And the rest of them, don't worry about that. So in this particular case, we were hoping to understand what's going on with this. Can we use the so-called cleavable side chain polymer to get higher conductivity? Because very rarely that polyethylene can give you high conductivity, except P.PSS, which is a very unique case. So in here, we using the traditional, if it's the TCS, the tertiary ester-based conjugate backbone, and then you can polymerize in the 4 different ways. You can make a random copolymer, the random copolymer. The regioregular polymer. This is a random copolymer. You can make the very regioregular material with the side chain pointing outside. You can make you can make the side chain pointed inside. So by and large, these 4 materials are isomers, because if you strip away the side chain, we're talking about polyethylenes. There's no thiolene, there's no side chain, they're all polyethylenes. The reason they're different is because how you decorate the thermocleavable side chain to the backbone. Okay, so once you take the material, you do the thermal heating, you end up with the same TGA as we talked about earlier. So about 20 degrees C, you can remove them all. There's no real difference among different materials because they're essentially using the same chemistry. On the other hand, if you're using the tryptophan acid, then you can use the acid to remove the side chain. This is the mechanism. But what's good in UCs is that now you can use a strong acid to remove the side chain at room temperature. That's actually pretty good, which we'll talk about in the next few slides. So let me skip this particular one. So now if you do the doping, remember doping, you need a dopant and you need a conjugate polymer, and you mix them all up. Some redox chemistry is going to give you the charge carrier density, then you end up with the conductivity. So F14CQ is a strong oxidant, which we often use to get the polymer being p-type dope. So now if you look at in here, it's interesting, right? So this conductivity is 10 to the negative 7, which is essentially insulating. If you put F14CQ to work with this material, you will increase the conductivity by 10 to the third, which is very good. Okay, but still, we're talking about 10 to the negative 4 conductivity, which is very low. So depending on the doping method, either you dip them, if you blend them, and you can slightly getting higher conductivity, but it's still very low though. If you take an FOTCQ together, you heat them all up, you actually end up almost no doping effect. This is because the FOTCQ under high temperature, as you are using high temperature to remove the cleavable side chain, FOTCQ also sublime. So you end up with no doping effect. Now you say, what about me heating polymer film, remove the side chain, and getting the side chain free polymer? Then you put in FOTCQ. But after heating, remove the side chain, your polymer film becoming so insoluble, essentially no diffusion can occur from FOTCQ into polymer film. That's why the very little doping can occur. So you won't be able to get a high conductivity either. So this is precisely what I meant earlier, that the thermal approach has a very strong limitation because of the high temperature. So the next thing we did was actually using the acid. That's where the magic is going to happen. All right. So same thing on the right panel, left panel. You do the heat, the same thing happens. Not much conductivity, and again, not much happening because of this thing. But once you do the triplet acid, remove the side chain, room temperature, something magic happening. You see, when you blend the triplet acid is also oxidizing reagent, they have some doping effect. If you put in the triplet acid together with FTCQ, if you remove them first, remove the second, you see some leveling off. You don't see much conductivity difference. But once you dip your polymer into the triplet acid and FTCQ mixed solution, you all of a sudden can make conductivity as high as 10. So if you go from 10 to -6 before doping to the 10 after doing this particular doping, you end up with the conductivity difference by 10 to the 6 or 10 to the 7. And that's the power of using the mixed acid plus FOTCQ. So that works across all the materials. So the purple pointing to this particular polymer, which does give you high mobility. So that's why after doping, you still end up with the lower conductivity because of kinks in here. And then if you have these two materials, you can actually end up with a higher conductivity after doping. But the true magic happens with the so-called PUETT2 because of the planar structure, and your mobility will be very high. And then because of this interesting doping, you have a higher carrier density, you end up with a very high conductivity, up to 500 in some cases. So that's what I meant, that even though you can have a thermocleavable side chain, but depending upon how you remove them and how do you process them, and you will end up with a different behavior. So that's why this particular. So you need novel materials. You need a cleavable side chain. You also need the interesting processing approach. Otherwise, you won't be able to get the highest performance. All right. So this is a summary. If you're interested, you can read this particular paper we published in roughly 1.5 years ago. And I realized I don't have much time, so about 5 more minutes. I'll be try to quick. Going through a few more interesting applications. So this is a second approach we did. We were using the partial cleavage to remove the side chain for the stable solar cells. So these are two papers we published a couple of years ago now. If you're interested, you can read them, but I will try to go through them very quickly. So the idea is very simple in a sense. It's because in the early days, 20 years ago, when Frederick Krebs were using this thermocleavable side chain, he essentially removed all the side chains. And he's starting with the side chain decorated polymer, you apply the heat, you remove them all. And he ended up with a very low efficiency because he doesn't even have any control of the morphology. So what we were thinking is that, well, perhaps we can try to making only partial sidechain control, because you possibly need some of the sidechain for the morphological control. But you also want to remove a lot of these other sidechains because you want to be able to increase the mobility and also carrier concentration and many other good features associated with the sidechain free polymers. So essentially, we're trying to mixing the sidechain free polymer with the sidechain decorated polymer in a chemical blend, if that makes sense to you. So it works really well. It works really well, and you can tell that if you are using the all sidechain decorated polymer Ph.D, you can get a high efficiency. Okay, it's about 3% in our lab. But once you Once you heat up the high temperature for accelerated testing, you will be reducing the efficiency dramatically, lasting about 90%, because your morphological is pretty fragile. When you get a high temperature, things can moving around and you're losing a lot of the efficiency. But if you're using the partial cleavage, you can get in the high VOC because you'll decorate the polymer with the carboxylic acid that will be reducing the hormone level and end up with higher VOC. But you also suffer from the smaller current because you still suffer from losing some morphological control. But the good news is that because the polymer is becoming so rigid, you only end up with a 10% loss because the morphology essentially being locked in with this partial side chain cleavage. So we're using this approach to some other don't accept the polymers. Well, same thing happens if you decorate about 60%, right? 0.6, that means the TCS 60, thermal cleavable side chain. Okay, TCS 60 with this particular polymer, you can gain very stable solar cell. But the problem again that your efficiency is not very high. It's only about 4%, okay, 3 or 4%. So, and very recently, we actually come up with an approach looking at this acid impact to the, sorry about that, I can't even go back now. Oh yeah, I'm coming back. So we were able to look at the pKa of the acid. We realized that this acid cleavage is actually depending upon the acid you're using. The reason is because that if you care, you can read this particular paper we published about a year ago. We derived the equation. We're showing you that by using the acid, you can reduce the activation temperature of the side chain cleavage from about 120 kilojoule per mole to almost 65 kilojoule per mole. So that means that you actually have a very good way. This is fundamentally why acid being applied is able to reduce the temperature you're using to do the cleavage. And that's also depending on the pKa as well. So if you're interested, you can look at the equation. You can predict your temperature by using the equation we derived. But nevertheless, what I want to show you is this is the most recent paper that I'm very proud of because it's essentially cultivated, essentially incorporated all the ideas we had in the past few years and with high efficiency. So you're taking this high performance polymer, we call D18 TCS, and then you using the acid, but not the triplet acid at room temperature, we're using the DPP, which is the phosphonic acid. You can apply about 140 degrees C. So if you mix them all up, and then about 30 minutes with only 5% DPP, you can lock in the morphology. You can end up with a 13% PCE, and you can actually having very high stability as well. So this is the most recent paper we published in January this year. So this just give you some sense about using the side chains. You will be able to also gain the high stability and high efficiency of the solar cell at the same time. So beyond the conductivity and the solar cells, we have spent some time to using this approach, this partial cleavage idea. We're able to make the stretchable multifunctional sensor. And most recently, we're using the similar idea to achieve the almost unity doping efficiency of the organic electrochemicals, OECT, omics, sorry about that. And that's something that we are still actively pursuing as well. So in summary, I hope you, at this point, you understand that why conjugated polymer needs side chains. We cannot get rid of that if you want to have the processing. So cleaving side chain will give you the improve the device performance and stability, right? So because you being able to increase the TG, the naked conjugate polymer is actually having a very high TG. So thermal and acid cleavage, each has pros and cons, as well as base and photo, all these things. You make the choice, okay, depending upon your intended application. So open questions including like residual-free chemistry, because at this stage, we always end up with a scar on the polymer, for example, carboxylic acid. And what about having a minimal interruption or disruption to the film morphology? Can we actually cooperatively design for new applications? So I think in the past, we talk about the side chains being passive because we treat them the way to improve the solubility, enable solution processing. But I'm hoping that of this talk, you possibly being able to give a new perspective to the side chain because this is essentially a temporary processing aid that can be programmed to remove. It can enable you processing, morphology, control doping, and can be partially or completely removed after film formation. So if anything that can stick with you, stay with you after the talk, and I think this is what I created this particular slogan or called myself, process with the side chains, but you want to be able to function without that. So with that, I want to thank the people who actually contributed to the contents of the talk today, and Sungwing and Stephanie, Jordan, Leon, and Gia. Many of them, a few of them already left our lab, but their research have been published. That's going to stay in the field. For the molecular doping, we actually have a Department of Defense supporting the MURI program with UNC, NC State, the University of Washington, and Utah. These individual researchers and PIs, and we spend a lot of time where we are having fun with the molecular doping project. And lastly, this is the two slides I will be using for the journal promotion. This is I'm the associate editor for the Polymer Science and Technology. And we pretty much publish all polymer science and technology related papers. That's why we call the polymer science and technology. You can tell, you can see from here, this journal scope. One thing that's I feel going to be very beneficial to especially people in Europe and the US is that these APCs are waived, okay, which means that anything you publish to the journal will be open access before 2028. So we have 3 open special calls, and here is you can see from here. So without I don't want to spend too much time talking about this, but thank you very much for your attention.